Okay, hi everyone. I think we'll get going. Oh, not sure what. Maybe I'm standing too close to Michael. Maybe is that a little better? Yeah, well, it's an absolute pleasure to welcome Michael Abdul-Masih to give a seminar at the CAB. Michael is currently a Lacaiccia Junior Leader Fellow at the IAC, at the Instituto de Astrofísica de Canarias in Tenerife. And Michael started his career in his native USA, where he completed his undergraduate and sort of master's, specializing in astrophysics, but not totally in astrophysics, right? Yeah. And then he was awarded a PhD position at KU Leuven in Belgium, where he sort of focused on massive stars that are literally in contact with each other. So after Michael's PhD, he was awarded an ESO fellowship, which took him to Chile, where he spent a lot of his time there as a support astronomer on the Very Large Telescope. At the end of this fellowship, well, for the fourth year of this fellowship, he took it to the IAC. And last year, he was awarded this very prestigious Junior Leaders Lacaiccia Fellowship, which is presumably the focus of this talk. So without sort of further ado, I'll let you take it away, Michael.
Thanks.
Thank you very much.
Can you guys all hear me okay? Microphone working? Perfect. Okay. Thank you very much for coming. And for those online, thank you for tuning in. As Lee said, my name is Michael Abdul-Masih, and I'm currently at the IAC. And today I want to talk to you about how we can account for the 3D effects of rotation and Roche distortions on the spectroscopic observables for massive stars. Okay, some weird feedback. So I primarily focus on massive stars. Get farther away from the microphone. Okay. Okay. So I primarily focus on massive stars. Massive stars are important for several reasons. When I'm talking about massive stars, I'm talking about stars that are more than 8 times the mass of the sun. They have strong stellar winds and high UV fluxes, which really drive the chemical and mechanical evolution of their host environments. So understanding how massive stars live, how long they live, and how they will eventually end their lives is very important for understanding the universe as a whole. And we can't talk about massive stars without mentioning deviations from spherical symmetry. There's a couple of different ways that we can get aspherical stars. One of the main ones is rotation. Rotation is very important in the evolution of massive stars for several reasons. It can lead to mixing, which is very important, as this will extend the life of your star and will also can change the evolutionary pathway of your star, and we'll get into that in a little bit later. And one of the big things that I'm focusing on with rotation is how it changes the 3D geometry of your star. So here I'm showing the kind of cross-section of your star at different percentages of your critical rotation. So at 0, your star is perfectly spherical, more or less. And then as you start rotating a little bit more, you get some ablation at the equator as the centrifugal forces push your star out a little bit. And as you get to critical, you can see that we almost get to this very lemon-shaped point for your stars. Now, one of the consequences of mixing one of the consequences of rotation that I mentioned is internal mixing. And there's a couple of different ways that rotation can cause mixing within your star and in different regions throughout your star. So first, normally as your star is evolving, the traditional picture that we all have is that as it evolves, your core will shrink, your envelope will expand. And due to conservation of angular momentum, this means that your core will start to spin up while your envelope will spin down a little bit. And this can lead to shear between the core and the envelope layers. And this can lead to some eddies and currents in here that allow you to mix material from your core region to your near, to your envelope in the near core region. And then also with rotation, as we change the geometry of your star, this leads to changes in your surface gravity, which then lead to changes in your temperature. And if your star is distorted, it can't be simultaneously in hydrostatic and thermal equilibrium at the same time. So what happens is that the star prefers to be in hydrostatic equilibrium, which means that it's out of thermal equilibrium. And to try to get itself back to thermal equilibrium, large-scale flows will start to occur in the envelope of your star. What will happen is that you'll have flows that go from the near core region up to the pole, across the surface down to the equator, and then back down from the surface down back into the near core region. There are many more mixing processes that happen inside of these stars, but I just want to focus on these two because these are very related to rotation. So just with these two, you can kind of see how we can bring material from your burning core region just to outside of the envelope with your shear, and then from your near core region up to the surface through these large-scale circulations, which we call Eddington sweep circulations. So why is mixing important? Why do we care that our stars are mixing? Well, for one thing, as you're mixing your star, you're bringing fresh material into the core. You can extend the lifetime of your star. And if the mixing is efficient enough, you can actually fundamentally change the way in which your star evolves. So as I mentioned before, kind of your normal picture is this top one where your core begins to shrink as it evolves and your envelope will expand until it reaches the end of the main sequence. However, if your mixing is efficient enough, you can enter the regime known as chemically homogeneous evolution. And as the name suggests, what happens is that your star becomes chemically homogeneous. You don't have a well-defined chemical core and envelope anymore. The mixing will allow you to mix the material throughout the entirety of your star. And an interesting consequence of this is that without this well-defined core region, the star doesn't expand as it evolves. It may actually shrink. So you can actually, when you consider a close binary system, this can become very important because it allows you to avoid situations where you would have a merger where in the normal evolutionary pathway, you would expect there to be a merger. So I'm going to pivot just a little bit and talk about massive over contact binaries. This is one such case where this kind of chemically homogeneous evolution can become very important. So the overcontact phase is expected to occur in about a quarter of all O-type stars. This happens when your two stars are so close to each other that they're sharing material and they're roughly shaped like a peanut. And there's many simultaneous physical processes that are happening during the overcontact phase. So you have exchange of material, you have tidal locking, you have mutual illumination, internal mixing, angular momentum loss through the winds, etc. So it's a very complex phase. However, we expect quite a few stars to go through this phase. And this becomes important because the physics that happens during this phase can have a large impact on what the future evolution of the system is. And unfortunately, we don't have many physical constraints or we don't have any quantitative observational constraints on these internal processes because we don't have many of them. We have about, if we go down to 8 solar masses and above, we have about 20 stars in total that are in this phase. And many of these haven't been studied in depth to understand how the mixing processes are happening in their core. Well, what's this stuff? So as I mentioned, the final fate is still very much an open question. As you tune the physics here, you can really change what the outcome of your star is. And these outcomes look very different from each other. For example, we have some cases where you can get to a BE star. You can get to a luminous blue variable. You can get to a blue straggler. You can also form magnetic massive stars through contact systems. Or you can form black hole systems and eventually get gravitational waves. One oversimplified way to kind of split these up is to those that are a result from inefficient mixing, and those are a result from very efficient mixing from chemically homogeneous evolution. And if we consider the chemically homogeneous evolution path here, remember that instead of the stars expanding as they evolve, they can contract. So what this means is that you can have a star that starts out in or a system that starts out in contact. If it's evolving chemically homogeneously, each of the two components will shrink within the Roche lobe and eventually come out of contact and allow you to form two black holes right next to each other without ever having to, or without the stars ever expanding. So this is one pathway that we have to actually form gravitational wave sources. However, it really relies on this chemical mixing. This is one of the things that I have also been focusing on, is trying to better understand whether this pathway is viable or whether this is just a theoretical, a theoretical model that doesn't actually represent what we're seeing in nature. There we go. So how do we actually look for this chemical mixing? Well, one thing that we're looking for is signatures that are happening from, or chemical signatures in the core that are making their way to the surface. So in the core, our stars are burning hydrogen into helium via the C&O cycle. And this is a catalytic process, and the total number of C and an O isn't changing, but the relative ratios of these elements are. So what we expect from the C&O cycle is that your carbon and your oxygen abundances will decrease while your nitrogen abundance will increase, as well as your helium abundance, because you're burning hydrogen into helium. So if we see these chemical anomalies on the surface, then we have a good idea that there's efficient mixing happening within the stars. So the deviations from what we would expect from the baselines give us an idea of how efficiently the star is mixing, if it is at all. And also mixing leads to increases in your surface temperature, and both of these two tracers we can detect via spectroscopy. Now here's where the little bit of the problem comes in, because we're dealing with stars that are not spherical. And all of our models for massive stars currently assume, well, they're 1D models, and they assume that your stars are spherical. So what ends up happening is that you have some interesting observational effects that happen when you have a distorted star. So as I mentioned before, your changes in your radius lead to a change in log G and a change in your surface temperature. So your star is going to look something like this, where you have a hot pole region and a cool equatorial region. But when we fit it with 1D models, you're assuming that it looks like some representative sphere of some representative temperature, some representative log G, some representative set of abundances. And usually what you would do is that you would compute your 1D model, and then you can evolve it with a rotational kernel to broaden your lines so that you get an idea of how fast your star is rotating. And this is kind of the traditional method that we have for fitting your stars. When you consider contact systems, this becomes more complicated. Again, here you have your contact system with the temperature structure across the surface. First, we need to separate the spectral contributions of these two stars. So you would disentangle them, and then disentangling assumes that your spectrum is not changing as a function of the orbit, that the only thing that's changing is maybe the light ratios. So you're approximating that you have two spherical stars in your system. Then when you do the atmosphere fitting, you fit each star individually. So you assume that you have two individual stars that are not affected by its companion in any way. And then you get out your stellar parameters and your abundances. So as you can see, this picture over here looks very different from what we started with. And this is one of the issues that we have when trying to fit massive stars spectroscopically. So how can we improve these techniques? One thing that we can do, we need something that can accurately model the geometry and the surface parameters of the star. And we also need a spectral synthesis code that allows us to accurately model the radiative transfer that's happening with these stars. So our approach is to combine two separate codes, each of which focuses on one of these components. So Phoebe is an eclipsing binary modeling code, actually, and it's primarily designed to fit eclipsing binary light curves and radial velocity curves. And Fastwind is a radiative transfer code, an NLTE radiative transfer code that's suitable for O and B type stars. And the idea is that if we know if we know the parameters of the star, in the sense that we can model how fast the star is rotating, if we have an idea of the stellar parameters, then we can generate a mesh that represents the geometry of the system based on the rotational potential, or in the case of a binary, the Roche potential. We can populate this mesh with local conditions such as temperature, log G, radius, radial velocity. So each one of these individual triangles has a set of parameters. And then what we can do is we can assign individual spectra to each of these patches across the surface. And then when we integrate over the visible surface, we get an integrated spectra or set of spectral line profiles that better represents the 3D geometry of the system. So it kind of is a cheeky way of getting around the fact that we don't have 3D radiative transfer codes at the moment. So we're kind of patching together a bunch of 1D models to reproduce what it would look like in 3D. We can do the same thing for contact systems. It's very, the exact same procedure, except in this case, we're not only using the rotational geometry, we're assuming the Roche geometry here for these systems. And here you can see that at any given point in time, any given phase, any given orientation, we can generate a spectrum or a set of line profiles that represent the system. So if we compare this to data, that star that I was showing you before, or that system, is VFTS352. It's an overcontact binary in the SMC. And if we take the solution that you get from photometry, from fitting a light curve and a radial velocity curve to the system, and then we calculate a SPAMS model. SPAMS is the name of the code. I don't know if I mentioned that. Spectroscopic patch model for massive stars, SPAMS. So if we fit a SPAMS model to each of the observed phases, you can see that without doing any fitting, just producing a model and seeing what we get out, we get a very nice agreement between the observed spectra and the modeled spectra. Of course, you can improve the fit by actually doing fitting and by adjusting the parameters slightly, because the temperatures and things that you would get from photometry are going to be slightly different from what you get from spectroscopy. So you can tune this a little bit and get an even better representation. So now we have a code that allows us to actually model the 3D geometry of the system. Now we can start to ask questions like, what happens if we, how does the 3D geometry actually affect the spectra that we're getting out? I'm going to switch focus to single stars just for a minute to make this a little bit easier to follow. So if we consider this rapidly rotating star, and I'm going to be using this a lot for the next bit of the presentation. This is a 40,000 Kelvin star rotating at 90% critical, in case you're curious. And here, if we look at this at different inclinations, so not changing anything about the star, just changing the perspective that we are observing the star at, you can see that kind of the way that the star appears changes by quite a bit. And if you squint your eyes a little bit and kind of imagine that you're fitting, or that you are creating a sphere that has the same parameters as what you would see here, you could say that this star, maybe you're seeing more of the hot poles, so maybe it would look a little bit hotter than if you're looking at a star with an inclination of 90 and you're seeing primarily this cool equatorial region. So yeah, the idea here is how it actually does this change. If we were to calculate a SPAMS model for each of these inclinations and then fit it with a 1D model, how would the temperature change? And this is actually what we find. So 40,000 Kelvin is what the input temperature is. And here, it's good to mention that here, with this kind of star, it's difficult to say. The temperature is changing across the surface. So what is the temperature of the star? What I'm saying is the temperature is a kind of surface averaged temperature based on the intensity across the surface of the star. So you can think of it as an intensity weighted average temperature across the surface. And that's a parameter that won't be changing depending on how you are observing the star. So if we compare that temperature with the temperature that we measure from fitting it with 1D models, you can see that we have quite a bit of a difference at most of the phases, or most of the inclinations of the system. Here I've simulated a signal to noise of about 300. And I have 1 sigma and 3 sigma error bars here. I've chosen 300 signal to noise because typically this is what we say that we need to be able to accurately measure the abundances for nitrogen, for example. So here you can see that with a signal to noise of 300, that for a majority of the inclinations, we are more than 3 sigma away from what the true value of the system is. So this is important because this means that potentially we're measuring our temperatures wrong when we have rapidly rotating systems. If we do this at varying percentage of critical rotation, so the one that I was showing you before was at 90% critical, but if we do this for a variety of rotation rates, you can kind of see this trend forming here. So you can see that at low inclinations, where you're seeing primarily the hot polar region, you're overestimating the temperature. Here I'm measuring this with the equivalent width of helium-1 over helium, of helium-2 over helium-1, which is a temperature tracer that we use for massive stars. But here's the corresponding temperature that it corresponds with. So you can see that as you increase your rotation rate, this deviation or this anomaly becomes stronger. And as you get closer to 90, you see that we start to underestimate our temperature by a little bit. So can we actually see this with observations? And the answer is yes. I mean, if we look at a set of overcontact systems and we model them with 1D techniques and then with spams, you can see that systems that have inclinations of about 90 or close to 90, you can see that spams measures a higher temperature and a higher luminosity. Yeah. Whereas inclinations of 55, you can see that there's more or less they're more or less equal. So you can see that this is an important effect that we need to account for. Another interesting thing that we can look at is how this affects the abundances, and this is kind of a little bit more counterintuitive, but the abundances are actually affected quite a bit by the rotation rate. In this case, I've chosen an example where this change in, or where this abundance deviation is quite strong. It isn't always the case, but in this particular case it is. And what you can see here is that our helium abundance, in this case, for almost all of the rotation rates, is underestimated by, in this case, almost a factor of 2 in the most extreme cases. And the reason that this is happening is if you consider how the temperature is distributed across the surface and how the ionization balance is changing across the surface, we're kind of probing this entire region of your equivalent width space. So pretty much here what I'm plotting is the equivalent width of your helium-1 line and your helium-2 line. This is a bit of a simplification, but I mean, ideally you would do this with many more lines than just 2. What you can see here is that as you're decreasing your temperature, you're changing your ionization balance, so you're getting more helium-1 and less helium-2. But if you look at the total equivalent width of both of those two species, we get a shape that's kind of like this. Now, if you consider that across the surface, the equivalent width that you're going to be getting, the total equivalent width of your helium-1 and your helium-2, is therefore going to be changing based on what your temperature is. So in your cool equatorial region, you'll be getting an equivalent width that's somewhere down here, 1.6. Whereas your hot polar region will be somewhere over here, again 1.6, and then right in this middle region here at about 40,000, you'll be getting a much higher equivalent width. What this means is that if you distribute this equivalent width over your star and then you average what your equivalent width is, you get something that's a little bit lower than what you would expect for a star that's rotating at, or that has a temperature of 40,000 Kelvin. And when you have a lower equivalent width, the way that we interpret this is that you have a lower helium abundance. So that's kind of what's happening here. What this also means is that if you have a star that's, say, at 30,000 Kelvin or 28,000 Kelvin, then you can see that we would always be underestimating, or that we would always be overestimating the helium abundance. So this will very much depend on what the shape of this curve is and where you are in your parameter space. So for example, if we look at nitrogen, it becomes a lot more complicated. There's a lot more species going on, and you don't necessarily have quite as nice of a curve as you do with helium. What that means is that right here, you know, maybe you're underestimating your nitrogen. Here, maybe you're overestimating your nitrogen. In one of these regions, it's kind of hard to say what the actual average will be. So this is just to show you that depending on where you are in your temperature space and how rapidly rotating your star is, you may be completely getting wrong abundances as well. Again, carbon, you get a completely different curve as well. So you need to, so this curve will change depending on which species you're looking at. So I mean, carbon, nitrogen, oxygen, helium all have their own curves, and depending on which lines of those species you're looking at. So the more lines that you include, you'll change this curve slightly. So yeah, it is really dependent on exactly how you're fitting your system and what parameters, or where you are in the parameter space. So great. Is there any more information that we can squeeze out of our spectra? Is there any other information that we're not using? The answer is yes. So one thing that we can do is look at the, wait a second. Yeah, one thing that we can do is look at the line shapes. So if you change your inclination and you plot your spectral lines here, you can see, for example, that in this case, your helium-2 line appears to behave more or less as you'd expect. It's just getting broader and narrower, but not much is changing with it. But if you look at your helium-1 line, you can see that it kind of starts to change shape at some point, and it doesn't look like what you'd expect a single star spectral line to look like. Come on. So, for example, if we look at it at an inclination of 30, this is what the model predicts that you'd get. And you kind of see we have this kind of double peaked helium-1 line, which doesn't really make too much sense, isn't really what you'd expect. But if you consider that your spectral lines are going to be generated by the surface, and if you consider that the strength of this line is going to there's going to be a bunch of different things that are going to kind of be competing against each other to determine how deep your line is as a function of wavelength. Okay. One thing is you have your stars rotating, so you have your blue shifted and your red shifted portions of the line. You also have your temperature. Your higher temperature, you would expect less contribution of helium-1. Lower temperature, you expect more contribution of helium-1. You also have the incident angle. So the parts that are closer to normal to the surface, you would expect them to be contributing more to the flux. So those kind of balance in opposite directions, what ends up happening is that as you move across your star in this direction in radial velocity space, you actually get a much higher contribution here in your helium-1 than you would in the center. This is another kind of weird effect that you would not be able to reproduce if you're trying to fit the star with single star models. Another interesting thing comes in when you consider the line broadening. So again, we're using that same 40,000 Kelvin star rotating at 90% critical. And here I just take a SPAMS model in blue, and I try to fit it with a 1D model in orange. And this is the best fit solution, and it doesn't look great. So the rotation rate, the real one that I put in, is about 630 kilometers per second. And what you measure is about 618 kilometers per second. So you measure an okay rotation rate, but you see that the fit doesn't look so good. And if we zoom in a little bit to try to figure out what's going on here, you can see that the helium-1 line, for example, the broadening appears to be underestimated, while if you look at the helium-2 line, the broadening appears to be overestimated. This makes sense, right? Because if we consider, there we go. If we consider the shape of, if we consider where these lines are forming, your helium-1 lines are forming primarily in this cool equatorial region, while your helium-2 lines are formed primarily in this hot polar region. So if you're not getting helium-2 forming down here, then you wouldn't expect it to be as broad as the helium-1, which is being formed across the entirety of the surface of the star. Looking at this another way, if we consider these lines and we move across each of these spectral lines to figure out where the contribution of the flux is coming from the surface of the star. If we look at the helium-1 line, we can see that we get very strong contribution from all the way at either end of the star going across. And you can see that it's very, very strong and deep in the middle of the star. But as you start to get up to the poles, it's a little bit less. The strength of the line is a little bit less. If we look at helium-2, for example, on the other hand, you can see that we almost get no contribution at the equator, and we get most of the contribution for the line up at the poles. And again, you'll see that you only really start to see the helium-2 line forming right about here. Right? So it's not actually forming across the entirety of your star, and therefore it's not getting the full rotation rate that you would expect from your star. So if we repeat this fitting and we allow for a different rotation rate between your helium-1 and your helium-2 lines, you can see that we get a much better fit. Still not perfect. If we zoom in, we can see that the helium-2 is more or less reproduced okay. We see that the helium-1 is still some weird stuff going on. But again, here we measure a rotation rate of 550 kilometers per second for helium-2 and 660 for helium-1. So this is a very big difference in the rotation rate that you would measure for these two species. And again, if you consider the shape of your star, what really is happening is that your helium-1 this is kind of where you would expect your helium-1 to be formed. So this is kind of where the contribution of your spectral line is coming from. And this is why you kind of get this kind of almost flat-bottomed spectral line, and why we aren't able to reproduce it as well. Whereas your helium-2 is formed almost as if it were a smaller star, where you cut out this middle region, and that's why we can still fit the helium-2 quite well. So this is great, but is this just a model, or can we actually observe this with real stars? The answer is yes, and the reason I chose these parameters is because we have a star in the LMC called VFTS 285, which has a rotation rate very close to that model that I was showing you. This one has a measured rotation rate of 609 kilometers per second. However, if you reproduce, or if you redo the fit and allow for a different rotation rate between your helium-1 and your helium-2, you can find that the helium-1 has a rotation rate of 617. Your helium-2 has a rotation rate of 567 kilometers per second. And even when you consider the errors, these are significantly different from one another. So this is a confirmation that we do see this in nature, and that this isn't just a theoretical case. Now this becomes very interesting if we consider that the ratio of the rotation rates of your helium-1 to helium-2 should remain constant as a function of inclination, right? Because what you're measuring here is V sin I of helium-1 and V sin I of helium-2, and if you take the ratio, the sin i's cancel out, and you're left with just the ratio of the rotation rates of each of those. What that means is that this is a direct measure of how rapidly rotating your star is. It's just, this is a way that we can measure the distortion of your star. So what this allows us to do is this would allow us to find the rotation rate of a rapidly rotating star and be able to say, hey, it's rotating at 50% critical or 60% critical or 70% critical without knowing the inclination. And there are very few methods that we have right now that allow us to find the inclination, or rather find the rotation rate of a single star without having some assumptions if it has a companion, for example, or for example, your BE star, you can do it based on the disk. So yeah, this is another way that we can do this. And as you can see here, you're more or less, as you start getting to lower inclinations, you start being dominated by other effects, other broadenings. But up to about, I would say, an inclination of 40 or even 30, you can see that we're almost completely independent of the inclination. So by measuring the ratio of the rotation rates, we get a measure of how distorted your star is. So what does this mean for internal mixing? Well, if we consider the Hunter diagram, which just shows your nitrogen abundance as a function of your V sin I, it's a bit of a mess. You see that we'd expect most of our stars to kind of fall along this region here, but we have some stars down here and some stars up here that we aren't able to reproduce properly. But as I've shown, if you have rapidly rotating stars, the stars where we expect the mixing to be the strongest, those we are measuring the temperature incorrectly and we're measuring the abundances incorrectly. So if, for example, we can replace this V sin I with the ratio of the rotation rates of your helium-1 and helium-2, then we get a direct measure of how fast your star is rotating. And if we correct for the abundances by accounting for the 3D effects, then we may be able to clean up this diagram a little bit. And this may give us a better idea of how actually these stars are behaving. Unfortunately, I haven't done this yet, so I can't give you the answer, but stay tuned, and maybe in the future, in a couple of years, we'll have better constraints on this. Okay, so what I've kind of described here, and the main takeaways that I want you to all leave with is that not accounting for the 3D effects can lead to incorrect temperatures, incorrect abundances, incorrect log Gs, which means that when we're trying to use these very distorted stars, which we expect to be the ones that are mixing the most, as tracers for internal mixing, we are completely biasing our results before we even start. So accounting for the 3D effects is super, super important when we're trying to deal with distorted stars. Also, there's extra information and extra diagnostics that we can squeeze out of our spectra if we kind of move away from the idea that we need to fit these stars with 1D. Even if you are using 1D codes, but you allow for different rotation rates for the different species, then you can start to get a little bit more information out of your spectra than you would otherwise. And this is a great way of doing a first sanity check to decide whether or not your star is actually rapidly rotating or is slowly rotating, but an inclination of 90 degrees, or whether it's rapidly rotating with a very low inclination. This is one way that you can kind of break that degeneracy that before we haven't been able to. And with SPAMs, we can provide corrections to 1D models for some parameters. And this is something that we're working on now to kind of provide to the community a kind of a conversion from your 1D parameters to what it would be if you corrected for the 3D. And I'll take this opportunity to kind of advertise SPAMs a little bit more and all of the things that you can do with it. It was written with contact binaries in mind, but it can do a lot. Pretty much anything that Phoebe can model, we can also model with SPAMs. We can produce a spectrum for. So I've showed you over contact binaries and I showed you rapidly rotating systems, but it can also model things like heartbeat stars. It can model semi-detached binaries. It can model regular binaries, for example, and some effects that we see in some of these systems. For example, the Struve-Sahara effect we're able to reproduce. Rosler-McLaughlin effect, which is very useful for those who study planets to actually measure how the line profile changes as your transiting planet is going across. Usually this is done fitting your radial velocity curve, but with SPAMs, you'd be able to directly study the line profiles themselves, which is quite an interesting application. Also, triples soon. I put that here because we're still working on implementing triples into Phoebe. And eventually also pulsations is another thing that we're working on. So being able to model pulsations as well with SPAMs. So I will end there, and I will thank you very much for your attention, and I'm happy to answer any questions that you may have.
Thanks, Michael, for the great talk. Thanks, Michael, for the great talk. Seem to be getting a little bit of feedback. Yeah, but I think that's resolved. I think it's really impressive what the work that you're doing, and this SPAMs code, which kind of joins these two sort of state-of-the-art codes and sort of smashes them together. I think is fantastic, and I'm sure the applications are, you put a sort of sample of the applications up there, and I think it really is quite widely applicable. This code. So I'm happy to take any questions in the room. I can see one already. So
thank you. Very nice talk. So I have a question about how large is the correction from 1D to 3D models. So have you quantified this? And is there for some parameters is more relevant than for other parameters?
Yes, so I showed you a couple. So I mean, here, for example, you can see the temperature in this case for a star that's at 40,000 Kelvin. Depending on the rotation rate, you can be up to about 3,000 Kelvin off, which is significant when we're talking about the parameters for massive stars. We can also do this for the abundances I showed as well. Go back. Almost there. Yeah, here. For the abundances, you can also see that that in this case for helium, we can be off by a factor of 2. So the thing here is that this is very much dependent on the temperature of your system. So to do this properly, what we would need to do is sample the entire parameter space, compute SPAMs models across the parameter space, fit them with 1D models, and figure out kind of how this varies as a function of temperature. I've showed you here an extreme case, but it's not clear if you're in other places of the parameter space, kind of how this would behave. So for example, we would know that here it would be extreme, but in the opposite direction. Here it is what I was showing you. But if you're over here in the parameter space with what your temperature of your system is, then it's not very clear to me right off the top of my head whether you'd be overestimating or underestimating, or by how much. So Your log G also changes. We have kind of corrections for that already, so that's a little bit less, I would say, pertinent right now, because we already have ways of accounting for the fact that we're looking at the log G, or accounting for the inclination when we're looking at the log G that we measure. But yeah, your temperature and your abundances will for sure be affected by quite a lot. There's also your rotation rate can also be affected a little bit, not quite as much. Even if you aren't accounting for the 3D effects, you're usually still within the right ballpark for the rotation rate, assuming that you are considering different ionization states when you're fitting. So, for example, if you are only considering helium-1, then you'll be off. But if you're considering helium-1 and helium-2, they kind of balance each other out a little bit. So,
Okay, thank you.
Thank you. Any other questions in the room? Or on Zoom? Or Miriam, would you like a question in the room or question on Zoom?
My question. Yeah, so we have the students on massive stars over there, and I would like you to please explain them what the effective temperature means in this context, whether it makes sense to use it,
yeah,
and what effective temperature you would use in the HR diagram.
yeah, sure. So I actually have a backup slide for this, exactly for this. So
I was not prepared.
Yeah, so the way that I'm calculating the effective temperature here, and the temperature that I'm calling the intrinsic temperature of the star, if you consider the Stefan-Boltzmann equation, and you rearrange this, your temperature that you're getting out is your luminosity divided by your 4 pi r squared, your Stefan-Boltzmann constant, all of that to the fourth root. Now, what we have here, this down here is an area. Oh, sorry, this is a surface area, right? So what we can do is we can calculate the luminosity contribution of each individual patch across the surface. So we have an area and we have a temperature. So we can calculate the luminosity that we would get out from that individual patch. And then by doing that, we get, yeah, the luminosity of this patch is equal to your area times your Stefan-Boltzmann constant times your temperature to the fourth. And if you sum over all of that, you get the luminosity. And then we can work backwards, where we know that this is just a surface area term. So if we get the total surface area of your system and you have your total luminosity, then you get out the temperature by coming back to here. So we get this L from each individual patch, and then we get the area by summing up the area of the patches. And then this is the temperature that I'm calling the intrinsic temperature for the system. So what this ends up being is very close to an intensity weighted average surface temperature. It's not exactly, but it's very close.
Okay, so, well, I guess the tracks take into account the fast rotation.
Yeah,
Okay.
well, yeah.
Yeah.
Yeah. So the ones on the HR diagram did account for rotation. So there I'm plotting the temperature that I'm getting out, but the problem is that with these 1D models, your temperature that you're getting out is not consistent with what you would expect of what's really happening with the system. So that's why you're seeing that the temperature that you get from SPAMS and the temperature that you get from the 1D techniques are different. It's just because SPAMS is accounting for these 3D techniques while the 1D models aren't. So your temperature measurement is incorrect.
So we have a question online, but the colleague didn't type it. So
I have a question. I don't know if you hear me.
Yes, I hear you.
Okay, so my question was about the law of gravity darkening that you are using.
Yes.
So what are you using? And I'm curious.
So I've done this with I don't know if I actually have a backup slide for this. I don't think I do. I am using for all of the plots, so for all of the plots that I've shown here, these are assuming the Espinosa-Lara 2011 gravity darkening prescription. If you do this with von Ziepel gravity darkening, everything is just a little bit more extreme in either direction. So Espinosa-Lara just makes these deviations a little bit less extreme. Whereas with von Ziepel, it's a little bit more extreme.
Sorry, I didn't understand what was your the law. Are you using the Van Ziepel law or something better?
No, I'm using something better. The von Ziepel doesn't exactly, it isn't how do I say this? As you start deviating from spherical symmetry, the accuracy of the von Ziepel law falls off. There was an updated prescription from Espinosa-Lara et al. 2011, which accounts better for the
Okay. I know, I'm the author of this paper.
Ah,
so-
okay, perfect. So then you know, yeah.
Yes. Okay. That's very good. Yes.
Yeah.
And you know that there is a yes, it's a good way to
Yeah. No,
make
it's
the gravity darkening. Okay.
Yeah.
Very good.
yeah. In the corresponding paper that I have with this, I compare the von Ziepel and the Espinosa-Lara prescription. So there I show how if you assume one or the other, how all of these plots change.
Yes, it's important for the for also the line profiles that
Yeah, definitely, yes.
sure. Okay, thanks. Good.
No problem.
Back on. So that, yeah, so we any further questions in the room? Don Pago.
Hi, Michael. Can you go back to the Hunter diagram? Okay, so you said that if you could use the ratio of the full width half maximum of the lines, get the stuff and sit up top. But the question is, what is, I mean, that you need another microphone. Yeah, so you need at least a certain amount of critical rotation to
Sure.
see these effects. So, and you know more or less how many stars
Yeah, sure.
are there. So what is your expectations of how many of those could be
No.
affected?
So yeah. I don't mean to say that we'll fix all of the problems with Hunter diagram. This will not be able to solve all of those. What I will say though, let me come back here just for a second. One moment. Okay, here. If we consider this case, for example, if we look at the rotation rates that we're having here, even already at 25% critical, we're already seeing a deviation from your helium abundance. It's small, but it's still there. So in this case, you don't necessarily need to be all the way up at 90% critical to start seeing some deviations. That said, I don't expect that we will be able to solve all of the problems or all of the, the issues with the Hunter diagram. But part of the problem here is that we're kind of comparing apples and oranges here. I mean, with the V sin I down here on this bottom axis, we don't really know whether we're comparing stars that are low inclination or whether it's a low inclination rapid rotator or whether it's a high inclination slow rotator. So I don't mean to say that we'll be able to solve everything, but what I mean is that we'll be able to get a much more consistent picture of what's happening. And as well with the nitrogen abundances here, these stars have different temperatures, and if they have different temperatures, then the change and then the abundances will be affected in different ways. So some of them may move up, some of them may move down.
So would that mean also that the very low V psi ones with the high nitrogen abundances will be most of them pull-on stars that just by chance you're...
I think the statistics say that that they can't all be pull-on stars. So yeah, there are other issues here, but we may get a tighter correlation along the center by accounting for this than we would otherwise. So it will help, I think. And I think it's important that we account for as many of these biases as we can to get a better picture of what's happening with the mixing. So
Okay, thank you.
Yep.
Okay, thank you very much. So Miriam, would you like to take a question from Zoom or your own question? There you are.
Very technical, very quick question. In the plots where you show the different helium abundances we would measure, what's the nominal helium abundance you use? Because
I use 0.2.
so initially, enriched,
Yeah, so initially enriched. So that was mainly just to show because
but if we observe it pole on, it's going to be decreased by more than a factor 2. Okay.
well, but yeah. So by pull on, so if you're doing pull on, then and you're at almost critical rotation, then you can see that it's behind the plot, but you're at about here. So I mean, it'll change by just a little bit with inclination, but yeah. The reason I chose 0.2, why it's so enhanced, is just the limitations of fast wind. Going down to too low of abundances in helium, I run into issues with the code. So I've chosen to increase my baseline just so that we can actually calculate the full range down.
Okay. Thank you.
Okay, we've time for possibly one or two more questions. So if there's anyone else here in the room, or anyone on Zoom, they can sort of raise their hand and we can unmute them and ask questions like that. No, well, one last chance for anyone in the room to ask a question. Well, if not, let's thank Michael again.
Thank you.